We'll talk about the design and development of Totem Pole. You can say 1.5 kilowatt Totem Pole converter, which is like how we have approached to the from the concept to the hardware realization, and you can say a simulation-driven approach. So I am Dr. Anup Singh. I'm working as a lead research engineer in Havels, CRI, Bangalore, India, and my colleague Ullas Vishwakarma, who has really worked hard on this uh, to get this product done. So we have used the simulation tool SIMBA. So we'll just explain like how we have utilize the software to make it through. So the agenda will be like a brief introduction about Havels, then what are the topologies, what are the control strategies we have used, and how we have done the firmware validation, what we have used in the actual hardware, and then detailed model simulation, and then finally hardware realization. Quickly about Havels India. Havels is a QRG group, so which was founded in 1958, headquartered in Noida, India, and it has 15 manufacturing plants. And QRG group includes total 5 brands under it: Havels, Lloyd, Crabtree, Standard Electrical, Srio, Havels Studio. And there are various business verticals. It has quite big market reach, and it has a lot of innovation and R&D centers. In financial year 25, it has filed 77 patents, including you can say 211 design registrations. So in revenue wise, it is around 20,000 crore of INR uh, in you can say in last financial year. So regarding the PFC and its totem pole PFC totem pole converter, I'll hand it over to my colleague Ullas, who will speak about the further presentation.
Good afternoon, everyone. Thank you, Anup sir. We are going to discuss on the totem pole PFC converter design and its simulation and its hardware realization. I am Ullas Vishwakarma. So, coming to its design, the typical low consumer application circuit majorly uses diode bridge rectifier as its front-end conversion circuits. So, as you can see from the illustrated waveform, the input current drawn from this circuit is not sinusoidal. Because of this non-sinusoidal current, its operating power factor is very low, which in turn draws more current to extract the same real power. So for this is not acceptable, like if the power rating of the end application circuit is very high, then it is recommended to operate that converter in a higher power factor so as to reduce the current drawn from the supply to extract the same real power. So this is where the power factor converter circuits are essential part of an application circuit. So moving on, so exploring the topologies of power factor conversion circuits, there are basically bridge, semi-bridge, and bridgeless topologies. So in the with the bridge converter, the classical boost uh, DC-DC converter is used as a power factor conversion circuit because of its easy to implementation with respect to control and the switching strategies. It has been mostly used, and it will give power efficiency of around 90 to 95% for most of its operation. Then the major disadvantage of this classical boost PFC circuit is that it is having the conduction loss in the bridge rectifier circuit. The To avoid this bridge rectifier circuit, the semi-bridge power factor topologies have been used, which try to reduce the conduction loss in the bridge circuit. But as you can see in the semi-bridgeless topologies, the semi-bridgeless boost topology, the input side bridge rectifier uses is being used for only 50% of of the conduction, while the interleaved topology entirely reduces the conduction loss in the inductor. Thus, even though these two topology doesn't reduces the power loss in the circuit, but it changes the location where the power loss occurs by reducing. And the major disadvantage of these two semi-bridge topology is that it requires two boost stages, and it has its own switching patterns and control strategies. So moving on, like we need to eliminate that input bridge rectifier to reduce losses. So we'll go forward with the bridgeless topology. So there is, based on the classical boost only, we have like improved version is the bridgeless topology, where the entire boost circuit will take care of the zero crossing part of the AC waveform, also performing the input current shaping. The only disadvantage is that the sensing parameter is like it is tricky to sense the parameters here, because the nodes the inductor current sensing is very tricky, because the node is floating here and it is difficult to sense that part. But to the next topology solves this problem by having a proper ground reference at the output, so it is easy to implement. So that is the totem pole topology advantage, and it helps us to reduce the conduction loss, where in this totem pole topology only two power switches work at any instant of time, thus reducing the conduction loss, also um, replacing the entire input bridge rectifier. So with based on these advantages, we have forwarded with the uh, totem pole as our design topology. So this is the totem pole design specification that we have used. We are targeting for 1500 watt at operating frequency of 65 kilowatts with the output ripple of 5%. So the converter design, the control strategy in the switching pattern is a very crucial part of the converter design. For this part, control design, we have gone with the PI based dual loop control system. The major important functionality of a perfector converter is to maintain a constant voltage at the output part and to shape the input current to match the waveform of the input voltage. Does it that's how it's like improves the power factor. So the inner current loop controls the inductor current, and the outer voltage loop controls the output voltage. So the way in which we are making the inductor current to follow the input voltage waveform is by embedding the input voltage waveform information into the control loop in a scaled manner. That's how we are able to control that part. In the switching pattern point of view, because this is a bridgeless topology, this switches needs to take care of the zero cross detection, and it needs to perform the rectification part also to produce the DC output voltage. So AC voltage zero cross detection and the polarity detection is a major point here in the switching pattern decision. So based on the control loop design, we have, with the help of SIMBA AC sweep test bench, we have designed our control loop, and we have like fine-tuned based on the hardware parameters, the gain parameters we have like fine-tuned with that one. And you can see this is the simulation we have done with the SIMBA test bench, and in the for the continuous domain. But for the actual system to be implemented, it has to be discretized, because it has to be implemented in the embedded firmware. So it is very crucial to map the continuous domain into discrete domain. That is where the C code block of the SIMBA has been very helpful for us, where we have implemented the exact control strategy what we wanted in a discrete domain in the C code, and we have like for each C code block, we can keep the particular sampling time, which exactly simulates the microcontroller operation. That's like that's how we are able to exactly simulate the real-time system in a without hardware. Next, this is the sensing algorithm. Uh, Sensing, as we know that bridgeless topology we are working on, so it is very much essential to have a proper working AC voltage sensing algorithm. So we have simulated that part also to to judge the effectiveness of the sensing algorithm within the simulation environment only. Next, so when it comes to simulation, most of the simulations are done for the steady state operation, but it is very much crucial to simulate the starting period of the converter. So that is where soft start algorithms or many other such algorithms are important, and that we need to simulate. So with the help of SIMBA, we have simulated that part, and as you can see, this is that transition period. Up to this transition period, the soft start algorithm will work, and that is based on this some sort of logic, and that logic dictates the different switching patterns that will be used within that soft start period. And after the transition period, the closed loop code will take care of the next part of the operation of the converter. The major major achievement major requirement for this sort of software algorithm is because of the presence of huge DC bus at the output side. There is a chance of high induced current. To protect the equipments and the switches, it is very much crucial to limit the induced current. That's why we have like implemented the software algorithm for that. Even before we have tested that effectiveness of that algorithm by varying the switching patterns even before realizing it in hardware and finalizing, and this has reduced our design time actually. So moving on, like, converter design is not fully completed without the thermal aspect of the converter. So thermal aspect simulation is very important because it helps us to finalize the heat sink sizes and material for the heat sink. So, but simulating the thermal is very much important. For that simulation, we have used the thermal parameter model supported given by the manufacturers for the MOSFET that we have chosen. Or otherwise, if MOSFET parameter thermal data is not, even though not available, we can use the datasheet parameters to derive the thermal data in a form of Foster models. So we have done that simulation, and this is the results. As we can see, it is constant at 110 degrees Celsius. Then moving on with the next simulation is like parasitics. Detailed model simulation is all about parasitics. Like it's very important to simulate the detailed model because even though we have simulated the control loop everything, it noise we can't eliminate in the hardware, and noise is majorly dependent upon the parasitics. So with the help of mm, SIMBA detailed MOSFET models, we have imported the MOSFET parasitic parameters from the datasheet directly into the simulation environment, and we have considered the PCB trace, PCB trace analysis, PCB trace impedances, and the gate drive section impedances, all those things for our simulation consideration. And we have this has been very helpful, like deciding the gate drive tuning of the gate drive section. As you can as you can see in the waveforms, without the tuned gate driver section, these are all the waveform for the gate drive part only, gate drive signal. With that, with with this result in mind, we have like recommended some improvements in the layout to our design team, uh, like minimizing the loop area in the gate section, and using a copper pad below the source of the uh, MOSFETs to reduce the parasitics, and like that. Then in the hardware realization point of view, these are all the waveforms we have got. Like for the after gate drive tuning, we have, based on the detailed simulation, we have reduced the ringing in the gate drive sections. This is the roadmap like we have used.
Thanks, Ullas. I think it was really a nice presentation. So the detailed waveforms, because of the confidential issues, we are not showing up here. And so this is it from our side. what we have used, how we have approached to design the complete 1.5 kilowatt Totem Pole PFC converter, which we are using in one of our application. Okay, so if any queries, we can take it up.